Hey everybody, here's your video notes breakdown real quick. We started off with reminding ourselves that if you know what the factors of a polynomial are, then you know the zeros. And we started off by mentioning today that the reverse of that is also true. That is, if you know what the zeros are, then you know the factors. So if you know a polynomial has these zeros, then it's got these factors. Okay, these are the factors of the polynomial that has those zeros. So synthetic division, as we said, is a way of finding those zeros as long as they are rational numbers. And that gets us to this thing called the rational zeros theorem. Here it is. You can read it. Basically, it's you're looking at the two parts of the polynomial and determining from those two parts what the possible rational zeros are. Okay, I'll let you read that. But here's an example. So let's say we have a polynomial x cubed 2x squared minus 3x minus 10. The constant is negative 10. That's the term at the end that doesn't have a variable on it, so that's the constant. The leading coefficient is the coefficient of the very first term, the one with the biggest exponent. And so you take the factors of the constant divided by the factors of the leading coefficient, and all the possible rational zeros for a polynomial come from this list. Okay? So in this case, with the lead coefficient of 1, there's only one thing on the bottom of the fraction. So it's just 1, 2, 5, or 10. This is the group of numbers that you would use in your synthetic division attempt to find the zeros. And it does work out that if you try positive 2, you do get a remainder of 0. So therefore, 2 is a 0, and x minus 2 is a factor of this polynomial. So if I want to find the rest of the zeros and the rest of the factors, I would start to look right here. 1 means 1x squared, 4 means 4x, and 5 is just 5. There's our new constant. So I've got this x squared plus 4 is plus 5. I would love to be able to factor that polynomial, okay, that quadratic, to find the factors and therefore the zeros. Because once you find one, you've found the other. But this doesn't factor. Doggone it. So my only choice then is to use the quadratic formula for this, and I've kind of I've shortened it up here a little bit. When you use the quadratic formula on this, you may have to look that up for your own to remind yourself, but I'll let you do that. You'll get this negative 4 plus or minus the square root of negative 4 over 2. Whoa, that's an imaginary number there. That's square root of a negative. So yeah, those are coming. Okay, imaginary numbers are part of this work that we are doing with polynomials. So we'll get back to this in a little bit later on. So here's another example where we did the same exact thing. Used the rational zeros theorem when we looked at the factors of the constant divided by the factors of the lead coefficient, and we made a list of numbers. In this case it was 1, 2, and 4, plus or minus 1, 2, or 4 I should say. And we found that for this polynomial's coefficients that negative 2 gave us a 0 and that positive 2 gave us a 0. And when we found those two zeros from this fourth degree, that means two more to find, because every degree is always the number of zeros. So fourth degree means 4 zeros. So we found two of them. Now we're going to find the other two by looking at this quadratic factor down here. X squared minus 2x plus 1. That does factor, hallelujah, to x minus 1 to x times x minus 1. So our two zeros there are 1 and 1. So there's the list of zeros. Here's a way to write it in factored form, and here's what it looks like in standard form. So there's two different ways to write the equation, and the graph looks like this. So we found out a lot of information there about that. Okay, so that was one of the things that we practiced a great deal today, is using synthetic division to find the zeros and therefore the factors of polynomials. We also touched upon complex numbers. And just to remind yourselves on some basics on that, I is defined as the square root of negative 1, which also gives us the fact that I squared is equal to negative 1. So please, please, please remember this. This is one of the most important things about this whole work here. I squared. But other powers, to continue a little bit with the exponents, other powers are interesting in a way that they repeat. So I squared is negative 1. I to the third turns out to be negative I. You can work that out. I to the fourth is 1. I to the fifth is I again. I to the sixth is negative 1. I to the seventh is negative I. I to the eighth is positive 1. In other words, these values just repeat every 4 values of an exponent. Okay? So that's an interesting pattern. very important about complex numbers is to think of them always as a plus bi form. And in fact, so obviously numbers like this are in a plus bi form, but even plain numbers like 5. 5 is a complex number, believe it or not. It's 5 plus 0i. All right? It's not trickery, it's just the truth. A purely imaginary number like 1/2 times I. That's also complex where the a part is 0. So a is the real part, b is the imaginary part, bi is the imaginary part. Now when you have two complex numbers that are written like this, 2 plus I and 2 minus I, and that happens when you use the quadratic formula, by the way, what you're getting is a pair of complex conjugates. This word right here, conjugates, refers to two complex numbers that have the same a value but opposite b value. Okay? And a very interesting thing happens when you multiply two complex conjugates together. By using the FOIL method, you end up with 5. Okay, 2 plus I times 2 minus I equals just plain old 5. No imaginary numbers. It's purely real. Multiplying two complex conjugates together gives you a purely real number. And in fact, if you squared the 2 and added 1, you'd get 5. So just keep that in mind. We'll do another one like that. Here's another one. And a place for using that. Let's say you had a fraction, 1 over 4 minus 3i. Well, if you multiply the top and the bottom by the same thing, that equals 1, so it's cool. You're not changing the value. But what happens on the bottom is you get 4 minus 3i times 4 plus 3i. Those are conjugates. It eliminates the real value, and what you end up getting, is 25. You get 16, 4 times 4, minus 9i squared. Minus 9i squared is the same as plus 9, because I squared is -1, so double negative. So you get 16 plus 9, which is 25. And again, it's this number squared plus that number squared. Before it was 2 squared plus 1 squared, now it's 4 squared plus 3 squared, but it's always the same thing. In fact, in general, anytime you multiply complex conjugates together, you get a squared plus b squared. Well, this is kind of interesting. This is a sum of squares. Right? We factored a difference of squares already. X squared minus 9, for example, is x plus 3x minus 3. What about, let me cover it up there for a second, what about x squared plus 9, a sum of squares? Well, let's say you had x squared plus 9 show up as one of the factors of your polynomial. Well, how would you find the zeros of that? Well, you would set x squared plus 9 equal to 0 and solve that equation. When you solve that equation, you get x equals plus or minus 3i. So that means x minus 3i and x plus 3i are factors. Once again, if you know the zeros, you know the factors. Okay? And so, so this polynomial could be factored so that it's x minus 1 times x minus 3i times x plus 3i. There's all three of your factors. Third degree, 3 factors, 3 zeros. 2 of them are complex. Let's look at factoring a sum of squares in general. X squared plus 16 would be x plus 4i times x minus 4i. X squared plus 5 is x plus I root 5 times x minus I root 5. We're taking the square root there, right? So that's all it is. We're doing the same thing. And you can, in fact, factor a sum of squares. That's about all we talked about today. Enjoy. Bye.